Thank you. So just for getting started here, is there anyone who hasn't heard of WebAssembly or WASM? All right, great, awesome. Is there anyone here who's actually had a reason to use WebAssembly in a production app? Okay, all right, so we're all about on the same page. I'd like to invite you back in a journey of time to the year 2017. Like most of you, I had heard about WebAssembly, but beyond some surface level stuff, I didn't actually know very much about it. I read this headline and I thought, well, I mean, I guess if WebAssembly really does kill JavaScript, then I'll figure that stuff out, but it sure seems like people have wanted JavaScript to die for a while now, and we're all still here. And besides, what does a typical JS dev need WASM for anyway? Well, little did I know, my experience was about to take a turn for the atypical. I work for a consulting firm based here in Seattle called Gen UI. We're in Fremont, and we do a lot of different kinds of work, but I think our dev manager described it best when he said, our web expertise is really in doing stuff that's a little weird. Last year, we had one of those weird client requests. And I'd like to tell you the story about how and why we built a screen recording and video editing app for Chrome OS that runs entirely client-side. Our requirements were as follows. The app was meant to look and feel like it was native to Chrome OS and act as a competitor to other Chrome OS screen recording apps out there. The client specifically requested that the app would provide video editing capability, and it needed to run locally offline. There are a couple of ways to develop for Chrome OS, and we decided to use Chrome packaged apps. On Chrome OS, packaged apps are essentially just web apps that are given some additional hardware-related APIs. At their core, they're just JavaScript, HTML, and CSS. As we started to investigate how we wanted to implement the project, I was actually surprised to discover just how much it's possible to do with media in native JavaScript. For instance, if the user consents, you can capture their whole screen or their webcam, and then use the native Media Recorder API to record that screen, create a video, and allow the user to download it to their machine. And that's possible in any web browser, any modern web browser. There's nothing special about Chromebook that lets you do it. So if all we needed was a screen recording app, then we'd be set with those tools. But the client had requested some video editing capabilities. And as a result, we started to get into a realm of things that are technically possible in JavaScript, but just not a great idea for a variety of reasons. For instance, if you wanted to create a watermark, you can create a media stream that collects data from a canvas element. You can then draw your watermark onto every frame of that canvas element and then merge it into the stream from your screen recording. But unsurprisingly, it's too memory intensive. So the resulting videos were kind of like watching a very badly dubbed foreign film. You've got all the pieces there, but they don't line up. Another of the video editing features we wanted to implement was trimming or shortening the video. It turns out you can actually do that in plain JavaScript, so long as you only want to trim the end of the video. If you want to trim the beginning, you're out of luck, at least in Chrome. And that brings us to functionality that simply isn't possible in native JavaScript. Once you create that WebM file from your media recorder, you're done. There's no way to add a watermark or a filter or something else after the fact. It's also not possible to re-encode the video. The Media Recorder API will give you a WebM. So if you wanted a GIF or an MP4, then you can't do it with native functionality. At this point, we went back to the client and we recommended a server-side only solution. And there were two big reasons for this. The first is that video editing is a memory-intensive process, and Chromebooks are not powerful machines by design. They are meant to do most of their work from the cloud. And the second is that really client-side video editing pushes the limit of what's even possible on the web today. We had 2 people working on this project. We did not have an infinite budget, and we wanted to deliver something reasonable. The client did take our recommendation into account, but ultimately asked us to move ahead with a client-side only implementation. This set us off on a journey to discover the limits of what's actually possible on the web today. Since we had already determined that video editing isn't possible in native JavaScript, we needed to find a way to run code that is not native JavaScript in the browser. And WebAssembly is by no means the first tool that allows you to do this. In fact, running non-JS code in the browser has a long history. Does anyone here remember a little thing, kind of obscure, called Flash? Anyone? Any ActionScript devs out there? What about Silverlight? Oh, shoot. I gave away my best joke. All right. You may have heard that WebAssembly isn't just another way to write plugins, and that's true. But without understanding a little more about plugins in general, it's hard to know why the comparison is even being made. So the 90s are in again. Let's go back to 1995. We are all wearing Jankos, and the Slater standing in front of you isn't me, but this guy. Yes, very good. Because you're living on the cutting edge, your browser of choice is obviously Netscape. And Netscape has just released the Netscape Plugin API, or NP-API. NP-API is the first way to develop plugins or browser extensions and to handle media from within the browser. What happened was the browser would come across content that it couldn't handle and detect the file type and then load the appropriate plugin. That plugin would run in place on your web page. As of today, NP-API is deprecated in every major browser. And that's mostly due to issues with complexity and security. It's also because the advent of HTML5 means that the browser can handle a lot of kind of things natively that would otherwise have been handled by plugins. But plugins didn't actually fully die with NP-API. In 2009, Google released the Pepper Plugin API, or PP-API. Pepper is a build chain that produces binary file types called native client and portable native client, or NACL and PNACL. Get it? Salt and pepper? Portable native client was meant to provide a more secure, less complex alternative to NP-API. With it, developers could recompile libraries written in C or C++ to a portable native client format, and then that could be run from within the browser and accessed in JavaScript. For those WebAssembly fans in the crowd, some of that may sound familiar. So why aren't we all talking about Pepper and how it harkens the death of the most widely used programming language in the world today? Well, an open standard for Pepper was never created. The resulting portable native client files were only ever supported on Chrome, Chromium, and Blink-based browsers. As of today, portable native client is deprecated for every platform, except Chromebook. But then, of course, we were building for Chromebook, so let's put a pin in that. That brings us to today and WebAssembly. Like portable native client, WebAssembly takes advantage of common hardware capabilities to deliver native or near-native performance. The mscript and build chain allows developers to convert libraries written not only in C or C++, but also Rust, into a WASM format that runs from within the browser. Developers can even write directly in WebAssembly for all you super nerds out there who just can't get enough of assembly language. Unlike Pepper, WebAssembly is an open standard, and it's been adopted by every modern browser. So it's really something that you can use and deliver to the vast majority of the web. But that doesn't actually say so much about what's great about WebAssembly in the first place, or why we'd want to use C or C++. There are really a couple of reasons why you might use WebAssembly in your application. The first of these is performance. Performance on WebAssembly in general is much faster than native JavaScript, and that's mostly due to a lack of dynamic typing in WebAssembly. Of course, if you're interested, there are many, many other talks that you can look into on the subject, and I strongly recommend Lynn Clark's cartoon introduction to WebAssembly, or for that matter, any of Lynn's talks. Due to performance considerations, you might look into WebAssembly if you have a particularly heavy operation that you could perform in JavaScript, but you would prefer not to. For instance, every single page web application framework that most of us in this room use has some kind of a DOM diffing operation. It's a heavy thing to do, and it can have negative performance implications for updating your page, particularly in component-heavy scenarios. Glimmer, which is the DOM rendering engine by the Ember team, has an existing build that leverages WebAssembly for this purpose. And that is a methodology that should ultimately result in a much faster rendering engine. And I am definitely not just saying that because Yehuda Katz, who is the primary architect of Glimmer, is speaking later today. There are folks who are looking into this for React as well. Performance aside, the second reason you might want to use WASM speaks to our problem with video editing. As we discussed earlier, you can't really edit video in JavaScript, but you absolutely can edit video in C++. In fact, you can do several things in C++ or Rust that are outside the current capabilities of modern browsers. That includes not just video editing, but also audio editing, platform emulation, and a number of different kinds of games. WASM was literally built for our use case, and so now we just needed to choose a video editing library that we could use. It was important to find a library because, as I mentioned earlier, there were only 2 of us, and we had neither the budget nor the expertise to build something by ourselves from scratch. It turns out there aren't actually tons of video editing options in either C++ or Rust, and that may be due in part to the tremendous popularity of FFmpeg, which is an open source multimedia library written in C++. FFmpeg is a command line tool that supports adding watermarks or trimming or cropping video or just about any other kind of thing that you might want to do with it. Our early research indicated that FFmpeg could be used through either portable native client or WebAssembly, and ultimately, we were unable to find another good candidate. Naturally, as JS devs, the first thing we did was go to the NPM registry, and actually, there is an FFmpeg JS. So let's take a look at that GitHub page. This looks pretty good, right? And actually, I am hugely grateful to GitHub user Kagami, who is the author of this package, and also Picture Romanoff, who forked it and added some extra documentation. Without these folks, we really would have been lost, but these were enough breadcrumbs for us to sort of figure out how to do this. But getting back to my NPM install, I saw a couple of concerning things right off the bat. First is the size. The entirety of FFmpeg, even when compiled, is about 15 megabytes. That is way too much to load when we're loading the app, and it is a lot to ask users to download from the Chrome store to begin with. The default build also includes tons of functionality we didn't plan on using. It also includes the H.264 codec, which as of last year was still patented. We needed a binary that was compiled without it. And second, the version of FFmpeg that this library is based on is an old one. This is a couple years old. So we came to the conclusion that even though there is an existing NPM install for this library, we still needed to compile our own WASM file. This is the point at which we started to get into technologies that JS devs don't tend to use on a day-to-day basis. And the first of these is called Emscripten. Emscripten is a build chain SDK just like Pepper, and for those of you who haven't done a lot of this kind of thing, it's vaguely analogous to a tool like Babel. Emscripten is a command line tool that takes uncompiled C++ library and builds it in such a way that a WASM is produced. You can pass in various build options when you use it, so if, for instance, you wanted to build your WASM binary in such a way that it's compatible with web workers, you would do that as a part of your overall Emscripten build command. So that's a lot of high-level information. Let's bring it down and take a look at something concrete. The following example is a little hello world written in C. Like most of you, I don't really program in C on a day-to-day basis or ever. But we can look at what's here and determine what it does easily enough. The main method is what runs when the app loads. We've imported the standard input-output library and then just used it to print our hello world. In a C application, this would print to your console. And actually, in our app, we'll print to the JavaScript console too, but we'll also display it in the DOM. Now we need to compile our hello world to a WASM file. You can do that in Emscripten by using the following command. You can see here that we do need to specify WASM, and that's because Emscripten can compile to other formats too, such as ASM.js. Also, -o output HTML lets Emscripten know that I actually want Emscripten to build my web page for me rather than just compile a binary. So let's take a look at that web page. As you can see, there's a lot more going on here than just hello world. By default, Emscripten's output gives you a page with a console that you can use to see the WASM output. In order to do this, it also generates some JavaScript glue code to connect the HTML with the WASM binary. So that seems simple enough, right? But if this were, say, a Thanksgiving turkey drawing tutorial, then we're at about this step here. we've drawn an outline of our hand. And you all know what comes next, right? We don't need Hello World. We need FFmpeg, and there are more than a few steps in between. But like every now and again, things just kind of work the way you think they should. So it's worth just trying to convert FFmpeg and see what happens next. First, we'll go over a couple of terms you may not be familiar with. Make is a Unix tool that acts as a task runner, just like gulp in the JS ecosystem. Clang is a front-end interface for compilation tools, and GCC is the GNU Unix compiler. These all work together to create executables for many C or C++ libraries, including FFmpeg. To get started, we need to pull FFmpeg down from GitHub. It's open source, so everything's there. This is the root folder of the FFmpeg library. What we need to do is use the project's make file and have all of those constructions and substitute Clang and GCC with our own mscripten build chain. Piece of cake, right? In case you really did think it was cake, please allow me to assure you that it is not. To help you out, mscripten has actually built their own tool that comes with their build chain and to help you substitute mscripten for GCC and Clang in C projects. It's called mconfigure. So first, we call mconfigure configure, and that will substitute mscripten for GCC and Clang. Next, we'll run mmake, and that should use our mscripten build chain for actually building the library into LLVM format bitcode. Assuming everything has gone well, this is the point at which we can run a command that's similar to our hello world command from earlier. But of course, everything has not gone well. After about 20 minutes of compilation, mmake has thrown an error, and it appears to generate from deep within the heart of this massive library. Anyone who's struggled to get their builds to transpile correctly using Webpack or Babel knows the pain that can accompany production builds, particularly as they become more complex. Building a project in C really is no different, and compiling that project into a format for which it was never intended adds an even greater degree of complexity. When we're looking at something like our hello world.c from earlier, it seems reasonable to debug the compilation process, even though we're not actually C devs. It did not seem reasonable to debug this giant makefile and delve into the heart of a legacy media framework. So let's make a long story short. mconfigure makes a number of assumptions about your C-based build environment that may or may not be true. For this particular makefile, it was necessary to go in and replace every reference to the existing build chain with mscripten. Second, mscripten can't use anything that uses ASM, not ASM.js, but just ASM. And that's used in many C libraries to provide compiler instructions to GCC. Since we're not actually building with GCC, we need to pass the option to build FFmpeg without ASM. Finally, mscripten won't actually convert every possible combination of things that can be written in C. We had to patch FFmpeg in a couple of places just to get the conversion to work at all. In the end, however, we did prevail, so let's take a look at a demo. Here, we're looking at a video that has been created in native JavaScript through a screen recording of a YouTube clip. Our media recorder has returned a blob that we can convert to a file and then save to the user's local machine. But you'll notice that we can't seek through this video, and that's not a great user experience. This is due to a Chrome-specific bug where their media recorder doesn't create keyframes as it records. Therefore, the kind of file that's created doesn't know important things about itself, like how long it is. Next, you'll recall that the client wanted to add trim functionality to our app, and that makes total sense from a user's perspective. We've all started screen recordings where we forgot to set up our screen and needed to trim out the first little bit. This is where FFmpeg comes in handy. When we rub our .webm video through FFmpeg, it'll add those missing keyframes by default. We'll also ask FFmpeg to trim our video to its desired length. When we're sending it to WebAssembly, it looks a little like this. I've compiled my FFmpeg build so that it works with web workers. And then I'll create a new web worker. I will listen to make sure that worker is ready, and once everything is loaded, I'll post a message that contains all the information that FFmpeg needs to kick off a trim operation. We can see that the type of thing that I want to run is called run, and that's the default or main method in FFmpeg. And I've passed in some data, which is actually as a array buffer. Finally, I pass in the same arguments that I would pass in if I were using FFmpeg from the command line. So we've got a -ss, that's where you're starting your video, -t, that's how long your video will be, and then -c copy just means we want to use the existing codec. Let's see what that looks like when it's applied to our video. All right, so I've kicked off the FFmpeg process by default in the background, and we can see that before too long, we get a little video. It's obviously different than it was before. It's only 2 seconds long. So that being said, there are some important caveats for using this technology. The last video editing feature requested by our client was to provide crop, and that's in case the user wants to only display a portion of what they've created in their video. And you can see we've kicked off our operation. We're getting lots of logging output from FFmpeg. That's great. We know that something is happening. But you know, like that video is only a minute long, and we're still watching it convert. So we obviously can't put that in front of a user. What's up? The other operations were really fast. And I told you earlier that performance in WebAssembly is supposed to be much better, right? Well, there are 2 things happening here that cause performance issues. And one is just that re-encoding takes a little more time than copying the existing codec. This operation would be a little slower from the command line as well, but not by a factor of about 1,000, which is what we have here. It turns out that when Emscripten performs its conversion, there are a few patterns in C++ that will convert, but have tremendously negative performance implications. For instance, code that relies on x86 alignment behavior, or code that makes use of setjump to save the execution context. And yes, I had to look that stuff up. So in theory, could we address these performance issues and patch them in the same way we patched the code that was causing conversion problems? Or maybe we could add in WebAssembly-specific compilation optimizations to compensate for compiling without ASM. The truth is, I don't really know. We did not have the budget to become all-knowing video encoding, WASM converting masters, and who does, really? It's also worth mentioning that when WebAssembly shipped to all major browsers, it shipped as an MVP. There's a ton of functionality coming down the pipeline that might help to support some of the issues we had with FFmpeg. One of these is multi-threaded support, which would almost certainly make the re-encoding process faster. WASM is also looking to support garbage collection, which will open the door to converting languages well beyond just C++ and Rust. Ultimately, since we were on the Chromebook platform, we took a look at using the Pepper build chain and portable native client. An FFmpeg conversion process is already well defined there, and the result is quite a bit faster than our WebAssembly binary. Although, perhaps unsurprisingly, the more performance-heavy conversions still take some time and still produce an unacceptable user experience on Chromebooks due to their lightweight processors. So, is this a story about why you shouldn't use WebAssembly? Not at all. We learned a lot, and I wanted to share those takeaways with you. First, FFmpeg was almost certainly the wrong library to start learning about WebAssembly and C++ in the first place. There are several existing WASM ports for popular C++ libraries, and you can find them on GitHub. Next, if you're evaluating a new C++ library that you think you'd like to use, then there are some well-known patterns you can check for to give you a good idea about whether you should proceed. Portability guidelines and API limitations can be found on the Emscripten website. And this is a case where it's a good idea to tap someone with some C++ expertise to help you determine whether your library of choice contains those patterns and how difficult it might be to patch them. Finally, the Rust language was specifically designed with the web in mind, and it looks to support WASM as a first-class compilation target. If the functionality you're looking for exists in both C++ and Rust, it's probably worthwhile to start with Rust. WebAssembly is an exciting new tool that opens a new world of functionality and performance, and it's helping to pave the way to using the browser as a true application platform. But for the average JS dev, converting functionality into WebAssembly is still a pretty big ask. It's tremendously helpful to have access to expertise in both the source code getting converted as well as the intended use of that functionality. As WASM becomes more mainstream, I expect to see better tooling, more libraries, and simpler processes become more prevalent. In the meantime, we may all be consuming WebAssembly through frameworks long before we ever have a reason to create anything ourselves. Thank you.